Okay. So, welcome to lecture 34. In this lecture, we will start a new topic, different formulation of classical mechanics, that Hamiltonian formulation. Okay. So, before that, let me recap little bit of last lecture. Last lecture was tutorial class, and in the tutorial class towards the end we are solving a problem to illustrate the Lagrange multipliers method for when two constants are present. So, let me I was in hurry towards the end because of time, and then we will start this new formulation. So, background is that we have so far learned Lagrangian formulation, and then another important topic of your this course Classical Mechanics 1 is the Hamiltonian formulation. So, if you have any difficulties, any question or particular any topic which you want to learn, please raise this issue in the discussion forum. So, we can discuss, but in Lagrangian formulation we will not consider anything else right now. We will move to the Hamiltonian formulation. But before we start the Hamiltonian formulation introduction, I will tell you that about the last problem in the last lecture. So, recap that a particle is constrained to move on a wire whose equation in cylindrical coordinate was given rho equal to A and Z equal to B phi. So, these constants you can write in terms of this notation, that A1 rho d rho plus A1 phi, sorry, A1 phi d phi plus A1 z dz equal to 0. And second equation I can write A2 rho d rho plus A2 phi d phi plus A2z dz equal to 0 in this form. So, clearly in the first case you can find that A1 phi is 0 equal to A1 z. Similarly, in the second case you will find A2 rho equal to 0, and in the first case A1 rho is 1. In the second case equal to, if you write B phi minus z, so you can write A2 phi equal to B and A2 z equal to, in that case, minus 1. Okay, or minus B, other case then. Okay, and then you have to write the Lagrangian. So, we wrote the Lagrangian L in the cylindrical coordinate, which was half m rho dot square without constraint now, phi dot square plus z dot square. Okay. So, this is the your Lagrangian, and then we often that equation of motion using the Lagrange multipliers method, which was del L del rho times ddt of del L del rho dot plus lambda 1 A1 rho plus lambda 2 A2 rho equal to 0. I am not going to write all three equation, but you can understand that if you have many constant, if you have more than one constant, then you have to use lambda, one lambda for each constant, and then this type of summation will be there. So, this will be the rho equation for rho. Similarly, you can have equation for phi, equation of z, but there will be 2 lambda. And solution will be given. So, there will be equation for phi. So, these 3 equation plus 2 constraint equation will give you the solution for rho phi z, and lambda 1, lambda 2. So, 5 variables and 5 equation you can find. Okay. So, I hope this problem is clear to you. So, let us move to the Hamiltonian formulation. So, so before that, let me recap or just remind you the silent features of Lagrangian formulation. So, important points. About the Lagrangian formulation. Some important, not all, but some of the points I will list down. So, we know the Lagrangian was function of qi dot and time, okay, and for I equal to 1 to n for the system with n degrees of freedom. Okay. So, for each I you have to find okay, then you have to find equation motion for each I, that will come later, and so this is first point. Second point is that you get a second order differential equation given by ddt of del L del qi dot minus del L del qi equal to 0 for I equal to 1 to n, 1 to dot 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 n. So, if you have a system of n degrees of freedom, then you will have n number of second order differential equation. So, if you solve a n number of second order differential equation, then there will be 2n number we need. So, we need 2n number of initial condition. I mean, what I want to mean that if you have a second order differential equation, then you will get a two unknown constant in your solution. So, to fix those two unknown constant, you need two initial condition, that the position of the system at t equal to 0, velocity of the system at t equal to 0 kind of. Okay. So, this and then third important that we have configuration space. So, in Lagrangian formulation we have configuration space, which is nothing but the space spanned by the all generalized coordinate. So, all generalized coordinate is one each mutually perpendicular direction, and if you can imagine such space, that is known as configuration space, and every instant of time system is represented by a point in the configuration space. Okay. And one more important point is that so you have a n dimensional configuration space, and you need 2n number of initial condition to find a solution. So, that point the system moves in the configuration space, means that point in the configuration space move from one place to another place. So, the other point I want to emphasize is that that whenever you calculate the partial derivative, so say qi and qi dot are considered consider independent while calculating the partial differentiation. Okay, that I want to mean. So, when we consider del L del q k, suppose I am differentiating Lagrangian with respect to a variable q k. In this partial differentiation, we consider other q I not equal to k and q j for all j are independent. So, q j dot for all j, q I not equal to k, all are independent. Okay. Similarly, when you consider the differentiation del L del q k dot, then we consider q dot I for I not equal to k and all q j are independent. Okay. That means q when calculating when calculating these variables are considered to be fixed. So, this is the meaning of considering q I and q I dot independent variables when calculating the partial differentiation in Lagrangian formulation. Now, Hamiltonian formulation, to introduce Hamiltonian formulation, we look for equation which is lower order differential equation. So, generally first order differential equation are easier to solve So, the question we are addressing, is it possible to have a formulation with respect to different variables such that we will get the first order differential equation, maybe more in number. So suppose if we want to go from this set of qi dot t to Hamiltonian formulation qi and say momentum to this and t, then is it possible to have the first order differential equation? Now, if we suppose it is possible, then we get first order differential equation, but the initial condition will be same. So, we still will have for the same system with n degrees of freedom that 2n number of initial condition. But now, if my equations are first order, then number of equation will be 2n, because one first order differential equation solution contains one unknown variable. So, still if we have two unknown variables in the theory, then we need 2n number of first order equation. Okay, so far what I said, that is it possible to find a new formulation where the equation of motion will be first order in differential equation, that we are looking for, and we will see that Hamiltonian formulation will provide the first order equation for the system. So, if you have a n degrees of freedom in the Euler-Lagrangian equation, we find there will be 2n second order differential equation. the Hamiltonian formulation we are going to develop will have 2n number of first order differential equation. So, it is natural that we can choose our Qi those the same numbers as the Lagrangian formulation. So, 2n number of variables we need. So, half of them will be the coordinate and half of them will be momenta, which will be, as we already know, can be defined from Lagrangian, that Pi Qi dot. So, in this kind of thing, then we can have to assign a new phase, new space, which is called phase space. So, concept of phase space will be there. Phase space will be 2n dimensional, because n coordinate and n momenta. However, I would like to mention that it is not invertible to take the half of the coordinates and half of them are momenta. So, to have a first order differential equation. Okay. So, now mathematically the problem to construct a system which will change the basis. So, Lagrangian we had the basis Qi dot t. Now, from here we will want to go Hamiltonian, which is Qi, Pi and t. So, this how we can go mathematically from Qi dot basis to Qi, Pi, t basis, and this can be done by the Legendre transformation. So, let us discuss about the Legendre transformation. So, we will consider the with the help of a simple example. So, let us consider a function 2 dimensional in f x y, and I can write this different 2 independent variable. F is a function of 2 independent variable, x y are 2 independent variable. So, df I can write as, by differentiation chain rule, is dx plus del f del y dy, which further you can write. So, let me write df as u dx plus v dy, where u is del f del x and v is your del f del y. Now, question is that can I go from this basis f x y, where x y are independent variables, to another basis where u and y, by considering another basis where u and y are independent variables. Okay. This can be, that means it is possible that I can go from xy basis to uy basis, and let us denote we can obtain a function u and y from this basis too. So, in G, this new basis, that u and y are independent variables. So, we expect dg will be del g del u du plus del g del y dy, right. So, let me put some equation numbers today, Legendre transformation equation number. So, let me write this is equation number 1, then I write this as equation 2, and then we write this as equation 3. Now, Legendre transformation says that I can go from xy basis to uy basis in this formulation. So, G u y will be f x y, say plus minus u x. The variable which are interchanging should be multiplied. This is the idea, but sign we will see that it can be plus, it can be minus, but we will try to find it. So, now if we calculate our dg using this equation 4, dg will be del f del x dx plus del f del y dy. This is because dg will be df. Then let us write, we have to fix that what will be the sign, what will be the appropriate sign, that we will fix. So, for the time being let us write plus minus sign. Then it will be x du and then plus minus u dx. Okay, let me back to the blue ink. Okay. Now, del f del u, because of equation 2 is nothing but your u. So, this is u dx plus v dy and then plus minus x du and plus minus u dx. Now, g, look at the equation 3, g is independent function of u and y. So, there should be dx term should get cancelled in this expression. So, if you choose a minus sign, then if you choose a minus sign, so sign we have to decide. So, now this will help us to decide our sign. This. So, if we choose a minus sign, then this will be x d minus x du, but this will be minus u dx. So, with a minus sign, this term will cancel with this and will landed with minus u x du plus v dy. So, this will be, and which is exactly we want, because g is independent function of u and y. So, it will have du and dy term, which we will have if we choose a minus sign. Okay. So, we can go from f to g provided. But so, let me write this as equation 4 now. So, equation 4 now we have seen that sign is minus. Okay. So, equation 5. So, let me put this as equation 5. Now, comparing equation 5 and equation 3. And equation 3, we find that del g del u minus x and del g del y is v. Okay. So, x is del g del u and v equal to this. So, what is the moral of the story at this point? That we can go from by Legendre transformation x y, where x and y are independent variables, to g, where u and y are independent variable, where u is del f del x. Okay. by a Legendre transformation G uy equal to f xy minus ux. So, this is Legendre transformation. This is Legendre transformation provided x equal to minus del g del u and v equal to del g del v. Okay. This Legendre transformation you are familiar, at least before coming to this course you must have done thermodynamics course, and in thermodynamics quite frequently you have used Legendre transformation. In thermodynamics you have moved from one set of independent variable to another set of independent variable. Sometimes it pressure, volume, temperature. Maybe from here you can go to the temperature, volume and entropy or quantities. So, always you use this kind of Legendre transformation in your earlier study. Okay. So, this Legendre transformation now we are going to use to go from Lagrangian formulation to Hamiltonian formulation. So, to go from the Lagrangian formulation to Hamiltonian formulation. So, what will be the structure of Legendre transformation? If I want to go to the Hamiltonian formulation from Lagrangian formulation. So, now we have qi dot t, and I have I equal to 1 to n for n degrees of freedom. So, there is multivariables function. From here I want to go to qi, pi and t. So, number of variables are same, but qi dot, the velocity will be replaced by the momenta. So, we have to write Legendre transformation keeping this in mind. So, what are the interchanging variable? That is important, because you must have noticed that x and u are interchanging. Okay. So, if x and u are interchanging, then we have in the Legendre transformation we have this product. So, what will be the Legendre transformation to construct Hamiltonian? It is supposed to be qi, pi and t should be, let me write this first. So, qi dot and pi are being interchanged. So, minus L qi dot and t. So, this will be summed over all I. So, when one variable being interchanged in the Legendre transformation, there will be one product term. Where two variable are being interchanged, there will be two terms. So, here we have n number of qi dot is being changed with the pi variables. So, you will have sum over qi dot and pi dot. So, this will be the Legendre transformation from to construct Hamiltonian from a Lagrangian. So, maybe in next class we will consider this transformation, and we will consider explicitly the Hamiltonian of the system. Okay. So, try to understand what I have said about the Legendre transformation in this class, and in next class we will be using this transformation to construct your Hamiltonian. So, the main motivation was that we had Lagrangian formulation when equation of motions are second order differential equation. So, is it possible to construct equations of motion which are first order? Then we will have a genuine advantage, because first order differential equations are easier to solve compared to the second order differential equation. So, maybe in the next class we will start from this point, this Legendre transformation, and we will construct Lagrange Hamiltonian. After that we will find that what will be the equation of motion, and for the simple systems we will consider we will construct Hamiltonian for various simple systems. Okay, so bye for now. So we will meet again for the next class, the lecture 35, to construct Hamiltonian from a Lagrangian through Legendre transformation. Bye.